Pluto was discovered by Clyde Tombaugh in 1930, and you can see my arrow here. There's this little this blob here, and that was discovered through a painstaking process of going through photographic plates at Lowell Observatory. And so the discovery of the system marked the discovery of the 9th planet of our solar system. And I'm one of the few who actually do continue to believe that Pluto is a planet, not a dwarf planet. We can have a discussion about that afterwards as well. To put this in a larger context, we have now, in this day and age, we now know about several dozens of planetary bodies that are the size of Pluto, and they're members of a region called the Kuiper belt, which is essentially you might consider it the debris left over of the formation of the solar system. And the Kuiper belt is essentially occupies a region of the solar system, over 40 astronomical units away from the sun. We being at 1 astronomical unit away. And this is an interesting system as far as the background is concerned about the origin of the solar system itself. These objects are probably the oldest and most pristine remnants of the formation stage of the solar system. So visiting them or coming across objects that are members of this class is very important because it gives us these direct insights as to what the conditions were when the solar system itself formed, some 4.5 billion years ago. So as you can see, Pluto is shown here and these are shown kind of relative sizes to each other, Pluto, Charon, and then the other, what are called common classes, the dwarf planets of the solar system. And these are all essentially populated out in this area here of the solar system in the red. So it just perhaps puts this in some larger context. Well, in 2001, a group of scientists, one of them who is sitting here in the audience, my colleague Kimberly Eniko Smith, she's going to give a talk right after me, won a proposal to send a lightweight spacecraft to Pluto itself. And this is a picture of the launch in July 2006. And just one of the coolest things to kind of keep in mind is that it was the fastest rocket ever. I mean, it reached escape velocity in under, I think, 10 seconds or something like that. You can correct me if I'm wrong. So it's one of these great feats. This is a sort of a picture of the instrument itself. This is the New Horizons spacecraft, and it has several instruments on there, ranging from radio detectors to spectrometers in the infrared, imagers in the infrared and in the visual band, and several other instruments, including a UV detector and a particle detector as well. And to put this in context, you can see the size of the spacecraft itself is approximately the size of a grand piano. So the dish itself is very small by normal standards, which is one of the reasons why you may have heard it took over a year to download all the data that we obtained from the close encounter of the Pluto system itself. It's basically like, remember the old telephone lines, 1,000 baud or something like that, the old dial-up. So essentially we had something like terabytes of data having to be downloaded at a slow trickle, which is the reason why it took so long to learn what we learned. But we learned a lot of things right off the bat. This is a trajectory of the spacecraft flight itself. It was launched, like I said, in 2006, and it passed by the Jupiter system about a little over a year after that, and undertook what is called a gravity assist. It flies by close enough to Jupiter that it feels Jupiter's gravity, so it slingshots it. And by doing that, you gain a lot of boost in power to get you to the next place that you're going. In that case, it was, of course, Pluto. It arrived at the Pluto system about July of 2015. And I was very fortunate to be on the Close Encounter team. It was one of the best things I ever did in my life, so I'm still in awe of the whole process and all the things that we discovered. So let me just give you now basically a picture walkthrough of the things that we saw. This is the cover of Science magazine that came out 2 months after the original, after the Close Encounter itself. And this is a low incident angle image of the southern end of what's called Sputnik Shot. And this is simply an astonishing place. And we didn't expect to see anything like this when we are making our closer approach. We thought it was going to be kind of like a bland, flat place with a big black spot in the middle, and maybe maybe a bunch of craters. And it turned out that this place is a low temperature physics laboratory, and it was just really astonishing. What I just wanted to point out, I'm not going to spend much time speaking about this, but you can see the atmosphere itself, and it actually shows hazes, which are, and the source and the origin of these hazes and how they're getting there. They're actually part of a lot of active research right now. But the fact that there's all this complexity already in the atmosphere was also something that we didn't quite expect to see. Let me show you a sort of full color image from the MVIC imager, which is color imager on the color in the visual band imager. And these are just showing the two bodies next to each other just by comparison. Charon is about half the radius, about an eighth of the mass of Pluto. It's like me and my 2.5-year-old son. We're about the same mass ratio. So that's how I kind of think about it. But the irony is, of course, Charon is a dead system. My son is definitely not dead, so that's a good thing that I'm there. But Pluto, being a much larger planet and is retaining more of its internal energy, is active, and I'm going to give you essentially a walkthrough of that. So I'm sorry, I'm going to give a little bit of short shrift to Charon, but maybe I'll give another talk one day about Charon itself. But Pluto is already just pretty incredibly fascinating from so many vantage points. This is an orthographic projection of the Pluto system as imaged. Now you'll notice that some parts of the planet, as this area here, this big whale, which is called Cthulhu Regio, and so dirty water ice exposed part of the surface. This area, of course, is not as well imaged, and that's because the spacecraft itself did a reconnaissance flyby, so it didn't go into an orbit, so you're just basically flying by and taking as many pictures from the side that's closest to the spacecraft itself. So it's in this area we have the most high-resolution image information. So I want to talk to you about the things that we saw and we discovered in that region, in that area. So, so this entire region is named after Clyde Tombaugh. It's called Tombaugh Regio. I'm going to talk about this region over here called Sputnik Planitia, and it's, like I said, a truly, truly astonishing place. It's a depression filled with nitrogen ice. This depression may have been formed from impact way back in the early days of Pluto's, back in the early days right after Pluto had formed, or maybe it was maybe a billion years or so later. This is also a matter of debate. But what's fascinating is that you see this area here, which is nitrogen ice. I'll talk a little bit about the properties of that. Here you see these, what are high-standing, 4 to 5 kilometer tall water ice blocks. And these water ice blocks, I'll talk a little bit about that in a minute. Hold on, I'll get around to that. First, let me just jump ahead here. The imager, the spectroscopes that we had on an instrument on the spacecraft called LISA, and it essentially did a surface cover analysis. At every point on the surface, we were able to assess what the composition was. So we see that it's covered with a lot of methane ice. Now, you normally think of methane, right? Cow pastures and stuff. But under these conditions, methane condenses into a very strong ice. And so we know that from this here, it's especially, the purple is to basically tell you where all the methane is located. Similarly, we can also do a scan of where the nitrogen is located. And the nitrogen is essentially mostly found here in this region called Sputnik Shot. And we also have locations up and around that also has pockets of nitrogen as well. Now, the regions in and around Sputnik Planitia, and this is on the eastern shoreline of Sputnik Planitia, abutting the highlands of the regional ship, and that's kind of, here's a picture kind of designating that. I just wanted to point out, this high-resolution images shows that there are these very strange and odd, high-standing structures, and up here in these highland regions. Down here in the plain itself, in the nitrogen ice, we see lots of these pits that have formed. What are the origins of that? We're not quite certain, but many of the ideas have been posited have suggested that these pits are actually formed through the process of sublimation. The nitrogen ice itself will sublimate away, and if you put a dimple into a surface that's sublimating, that dimple will grow faster or sublimate faster than places that are flat. And so these things tend to want to grow. We have examples of that in very, very dry climates. Like, I don't know if any of you have been up to a place called like the Atacama Desert in Chile. It's a very, very dry climate, but it's also very cold, and you'll see patches of water ice that will form what are called penitentes, and these pits that form. And they look like these ice structures as if they're praying to the heavens. And so we think that similar types of processes are at play here in the nitrogen ice in the plains that we see down there in Sputnik Planitia. This is a fantastic image. This is a color composite kind of draped on the spherical surface. It gives you a sense of the variety of structures that we see. I just want to point out here in this region, we see a lot of these water ice blocks that look like they've been rendered free from the edge of the highlands here and then drifted in, or are in the process of either drifting in towards the center of Sputnik Planitia, or maybe they're being pushed out. Hard to tell, but that's also currently a world of debate. Sputnik Planitia itself gives you a sense of scale here. And you can see the discolorations here. This is the black, the maroon colored material here is a lot of dirty ice that I mentioned. Here's another more southerly view, kind of similarly to the one we saw before. So this is the southern end of Sputnik Planitia. So yeah, and by the way, all these images can be found on the NASA website in one form or another. So if you ever get a chance, you go to the NASA imaging site. There's several links to that. You can just go to NASA itself and say NASA Pluto images, and all these things will show up. So I give you my PowerPoint, but that's probably hard to hand it out to you all. Just give you a sense here of the water ice blocks that we're dealing with. Now, the surface temperature of Pluto is at 37 Kelvin, or to use familiar gauges, almost negative 400 Fahrenheit. So it's cold. You know, there's no way to dice it. But the interesting thing is that nitrogen under these conditions forms in ice, and it actually does something quite fascinating, which I'll get to in a little bit. But one point I wanted to make, that nitrogen ice, as an ice, has the consistency of something between very thick tar called bitumen. Maybe you've heard of that expression used. So it has a consistency between bitumen and water ice on the Earth. So it's fairly malleable on the length scales that are of interest to us. And that's why it's interesting in the sense of it also is malleable, means to say that ice blocks are literally floating in them. Because water ice is less dense than nitrogen ice. Nitrogen ice actually is a lot heavier, a lot marginally heavier. It's marginally more dense. Therefore, it actually can support these what appear to be blocks of basically icebergs. It's pretty fascinating. This is a blow-up region of around Sputnik Planitia itself. And I wanted to show you this just so you get a sense of the complexity of the geology that's there. In this region that there's hardly any craters. So that means to say that if there are no craters, it means to say that the surface is being resurfaced, literally. It's being paved over on a time scale that's pretty fast. Because many other bodies in the solar system that are not surface active, you'll see there are craters left over from the very beginning when the surface was hit, and then just sit there. But here, those craters are being covered up, they're being encrusted over, all kinds of processes are going on, so which is why we never really thought that this is an active place, even though it's so cold. So it's so fascinating for so many reasons for that. And so this here is work that was done by one of our colleagues, my very good friend, Oliver White, who also works here, who's on the mission. And he did a detailed geologic mapping of this region. So it just gives you a flavor of all of the various types of things we're seeing on the surface. Of interest to me is this region, these what are called these ovoid patterns you see on the surface of Pluto, and this is indicative of the fact that the nitrogen ice itself is experiencing what's called buoyant convection. Let me say a few words about that. What you see in the middle of Sputnik Planitia are these patterns. You can see almost this nice hexagonal pattern example over here. You see others as well. And it turns out that nitrogen's ice, even though it's an ice, it is malleable. And it also turns out that Pluto's interior has a geothermal flux, just like the Earth does, like all the rocky terrestrial planets, has an internal source of energy. Although it's much lower, it is enough to heat the base of the nitrogen ice layer, causing the base to become slightly less dense and having it rise. And what you see down here is a simulation of that, of nitrogen ice, but you can see the time scales involved for the overturn. It takes thousands and thousands and thousands of years for the thing to go up. But essentially what you're seeing here is that the red here is the ice that's been warmed up, becomes slightly less dense, and is rising to the surface. But just like a conveyor belt, it's got to make way for the other ice coming behind it. And so you get what sets up is this giant conveyor belt, and what we're seeing here from the top is an example, is the expression of that action from the surface, on the surface. So it's so cool, and what's awesome is that we've not seen this in any other place in the solar system, exposed on the surface like this. We know that the Earth's magma and the Earth's interior is undergoing similar types of buoyant activity like this. And that's what causes, say, the plates on the Earth's surface to move around or whatnot. But here we're actually seeing it literally exposed on the surface, which was something like, we were like, whoa. Like, we never thought we would see that. And it's funny, interestingly enough, I mean, back in this, my thesis work in grad school was on these types of processes, of course, probably to the sun. So when we got that image that morning, we were looking at it and like, oh my God, it's convection. Who thought of it? You know, it was like, so it was really cool. For me, it was way cool. What I'm working on a lot these days is this examples. We see nitrogen ice glaciers flowing on the surface. So you see, here's a colorized picture of Eastern Tomball Regio, where the colors here indicate relative topography or elevation. And if you look very closely in this zone right here, you'll see examples of streamlines that are associated with the actual flow of glaciers. Now these glacier flows, just like on the Earth, takes hundreds and hundreds of years to advance. On the Earth, it's a little bit shorter time scale, but they do move slowly. Here's an example of a glacier on the Earth, and you can see examples of what are called medial moraines, and you see exactly similar examples of medial moraine action down here in this sort of throat and channel. So it's it's wonderful that we're actually seeing an actual active example of glaciation on another planetary body. So this alone was a treat. This alone was a reason to be alive and to see that, you know. But there's all these other cool things too. So let me show you a couple other things. There's examples of past glaciation on the surface, and many of these. So there are these various types of geologic features on the surface that hearken to glaciation on the Earth. Let me give you an example. There's a region called mountainous dissection. And this is a section of the the northeastern section of Sputnik Planitia, which is sitting here. And these are the highlands. And you can see these striated patterns here, and these are very similar to the kinds of what we call fluvially dissected patterning on the Earth's surface as well. So, am I good? Like 2-3 more minutes? Okay, I'll make it quick. So here's an example of another glaciated valley, very much similar to the Yosemite Valley itself. So I'll kind of give you a sense of like similar types of structures that we know just in our own state are actually clearly present on Pluto. It's a possibility of water ice mountains, what are called cryovolcanism. It's very possible that we see these what are clearly mountains made of water ice. It has this elephant skin texture, and they look like they may have formed through the process of volcanism, but whereas on the Earth, volcanism is driven by silicates coming up from the Earth's interior, this is actually water ice, water probably in a liquid, slushy state, making its way to the surface and then freezing out. So that's pretty cool. And we also see examples of tectonism on the surface. I could talk a little bit about that, but I think I've run over my time. There are these structures we've never seen anywhere before called the bladed terrain. These are these literally terrains that have structures that look like blades, and they're made of methane. How did they get there? We don't know. So that's kind of one of the things that we're like studying right now, trying to make sense of that. There's this region here, what's called Scarpered Sheep, in this region called Planitia, named after an Ottoman admiral, if anyone ever asks. And and you can see here that this is made of water ice, but the floors are, the surface regions here, where the purple is indicated, is made of methane ice, but what's left behind is actually water ice. And so one of the ideas that we think that's going on here is that these are like the Badlands in Wyoming, where there are these structures that are sublimating off the rock, and the rock is collapsing and leaving behind debris. In this case, debris is water ice. So that's my last slide. I just want to keep you guys aware of New Horizons is still hurtling out into the solar system, and it will visit a Kuiper belt object about 30 kilometers in diameter. And that visit, that flyby, will happen next January, so in about a year's time. So do stay tuned. You'll be hearing a lot about that. And this will be beautiful because it will be the first insight into the oldest, hopefully most pristine object left over from the formation of the solar system itself. So we're going to learn a ton of new things about our origins in this process. So thank you very much, and I'm sorry I've gone over.